Hi, welcome back to Calculus. Today we're looking at section 4.4, concavity and curve sketching. So concavity is going to be the last piece that we need in order to be able to start just making some really nice graphs. So we need a definition of that, and then we'll go on into some ways to find concavity and making graphs. So the definition says the graph of a differentiable function y equal to f of x is A, concave up on an open interval I if f prime is increasing on I. Now, so you have an original function f, and it's concave up if its derivative is getting bigger. Again, this doesn't mean the derivative is positive, it just means the derivative is increasing. It's concave down on I if f prime is decreasing on that interval. So now we're going to get the second derivative test, and that's going to help us figure out concavity, and we're going to talk about some other wonderful stuff. So here we go. Okay, so the second derivative test. This just says let y equal to f of x be a twice differentiable function on I. So on this interval, whatever it might be. Then one, if f double prime, so the second derivative is greater than 0 on I, then the graph of f is concave up. If f double prime is less than, oops, I forgot my 0 there, less than 0 on I, the graph of f is concave down on I. And as a definition here, a point C, f of C, where the graph of f has a tangent line and changes concavity, so it goes from concave up to concave down or vice versa, is called an inflection point. And these happen, not terribly shockingly, where that second derivative is either 0 or does not exist. And so when we start making graphs here in just a few minutes, we're going to be looking for those critical points so we can get the max and mins, and we're going to be looking for inflection points so we can get the places where concavity changes. And that's really what we'll be looking for. So we still have more to get to. I promise I have some examples coming. We're in the middle of all this just kind of me talking stuff right now. So yeah, I've got another piece to the second derivative test for the next board. All right, so the rest of the second derivative test. If f prime of c is equal to 0 and f double prime is less than 0. So your first derivative is 0, you have a critical point. We want to know, is it a maximum or a minimum? Well, if the second derivative is less than 0, that means your graph is concave down. Concave down means it's got to be a maximum value. So you get a local max at x equals c. And if f prime of c is equal to 0 and the second derivative is greater than 0, then you have the opposite case. It's concave up. F is going to have a local min at x equals c. And finally, there's a third possibility here, and this one's not super fun, but it works, or rather doesn't work actually. It says if f prime of c is equal to 0 and f double prime of c is 0. The test fails. The test is basically inconclusive. The function may have a max, a min, it might have neither. We don't know. So, yeah, the second derivative test for max and mins only works if the second derivative is less than or greater than 0. All right, so on the next board, I'm going to put some things to look for when you're graphing, the things you're going to want to put on graphs, and then we'll do two examples where we make some pretty fun graphs. Okay, so I have the directions here for making graphs, and as you're going to see, there's a lot of stuff that goes into this. Basically, we're going to find a whole pile of points. We're going to put them on the graph, and then we'll connect them to make some really nice graphs. So first of all, figure out what is the domain. Is this function defined for all real numbers, or does it have some zeros in the denominator that are going to blow it up, or does it have a square root so you can't have those negative values inside of it? What is your domain? After you think about that, find the first and second derivatives. Okay, we're just going to get that done. We're going to get that out of the way so that then we can just do a whole lot of algebra. After you find the two derivatives, find your critical points, which you will then use to figure out where the function is increasing and decreasing, as well as any max and min values. And you're going to need full ordered pairs for both of those because we want to actually put these points on our graphs. Then use that second derivative to find your inflection points and determine where the function is concave up and where it is concave down. Finally, consider the question, are there any asymptotes? So again, if you have zeros in the denominator, high probability you have a vertical asymptote. If you have a rational function, you're going to get some horizontal asymptotes. Or if you have an exponential function, you'll even have a horizontal asymptote. And then plot all those points. Plot the critical points, the inflection points, and go back and find and plot those x and y intercepts, and then draw your graph. So I have two examples. They're both going to take some serious space, probably more space than I've got on this board. So you're going to need to just kind of pause and get everything written down each time on the board, and just keep it because I'll have to keep going. All right, here we go. All right, so here's my first example. Well, let me rephrase that. Here's the beginning of my first example. Again, make sure you get all this written down because I'm going to just be using some of this information later when we make the graph. So I want to graph y equal to 1 minus 9x minus 6x squared minus x cubed. This is just your basic polynomial. It's a third degree polynomial. So its domain is going to include all real numbers. Right? We don't have any division by x. We don't have any square roots. So everything's going to be allowed here. So I went ahead and took the two derivatives. The first derivative ends up being negative 9 minus 12x minus 3x squared. And the second derivative is negative 12 minus 6x. So I have those. I'm ready to use them. And let's start using that first derivative to find the critical points. So I take my first derivative. I set it equal to 0. And when I do that, I need to solve this. You could use the quadratic formula. I chose to factor it. I noticed that all three pieces were divisible by negative 3, so I factored that out. And I put the x squared first because I just like it better that way. And once I did that, I was able to factor it then to be negative 3 times x plus 1 times x plus 3. You're more than welcome to check my factoring. Pretty sure that it works. And that gives me x values of negative 1 and negative 3, setting these two pieces equal to 0. So to finish up the critical points, I just went back in and plugged negative 1 and negative 3 into the original function because I want to know where these points are so that later I can put them on the graph. So I plugged in negative 1 and got 5, so I have the ordered pair negative 1, 5, and I plugged in negative 3 and got negative 3, 1. So those are my two critical points for this graph. Like I said, we'll need those later on when we actually make the graph. All right, let's continue. Okay, so here is my continuation of that problem. Notice, still no graph, which means there needs to be at least one more board to graph this. I think one more will do the trick just fine. So first, I identified, we had those critical points from the last board at x is negative 3 and negative 1. I identified that they were mins and maxes by testing points in those intervals again to see if the derivative was positive or negative. So if I plugged in something out to the left, we got that the derivative was less than 0. In the middle, it's greater than 0, and out to the left, it's less than 0. So negative 3 ends up being a local minimum, and negative 1 ends up being a local max. And we have that it's an increasing function from negative 3 to negative 1, because that's where the derivative is positive, and decreasing on those other two intervals because that's where the derivative is negative. So then I moved on to inflection points. So for the inflection points, remember we take the second derivative, set it equal to 0. In this case, if you do that, you can solve it, you're going to get negative 2. When you plug in negative 2, you get 3 for y. Again, this is in the original function, and so we get the ordered pair negative 2, 3. That's going to be our only inflection point. And using the second derivative test, I can figure out where it's concave up and concave down. So it turns out the second derivative is positive to the left of negative 2 and negative out to the right. And so I have my concavity. It's concave up from negative infinity to negative 2 and concave down from negative 2 out to infinity. So the last piece that I needed for this problem was a y-intercept. I plugged in x equals 0, and if you do that, you get y is equal to 1. So go back to the original function, which I don't have on the board right now, plug in 0, and you're going to get 1. When you look at the x-intercepts for this problem, you have to take this third degree polynomial and try and solve it. That's a lot of work. It can be done, but it is a lot of work. So we're just going to say, you know what? I think we have enough points. So if your x-intercepts are really nice and easy to find, go ahead and find them. If they're kind of a mess, don't worry about it. So I'm not going to worry about it. So now we have all of our points. We have our y-intercept, we have our inflection point, we had, on the last board, we had the critical points, and now we're just going to put it all together and make a lovely little graph. So hopefully you have everything written down. I'm going to make a graph. Okay, so here's all of our information. We have, again, all of these points. I didn't show the increasing and decreasing in the concavity. Go back and look at the, hopefully what you wrote down for that, but it all fits together. I promise it does. So go back and compare my increasing and decreasing and concavity. So you can see I have my minimum value here at -3.1, my max at -1.5, the y-intercept at 0.1, and there's my inflection point at -2.3. It goes from concave up to concave down, and it goes from decreasing to increasing to decreasing, and I'm pretty sure it matches all of the information that we found. So there is that example. We have one more to do, but I think it's probably going to take me longer than YouTube will allow. So I'm going to end this video and I'll make one more video for that last example. So come back and watch that other video.